This is a set of planets. This is a set of frogs. This is a set of wigs. So a set is just a collection of things. In everyday language, a set is often used in the context of, for example, a set of golf clubs or a set of cutlery. In those situations, the items in the set usually have a number of particular roles. Like there's a driver and a putter and whatever. That's not the case in a mathematical set. Mathematical set doesn't have a group of things which have particular roles. It's just an arbitrary collection of items. The idea of having a group of things which each having a particular role mathematically would be called a tuple. So we're not concerned with tuples, with things with particular roles or purposes. We're talking about arbitrary collections of items. So we can have sets of anything we like. They can be physical objects like wigs or cats or planets, or semi-concrete objects like triangles, which might be thought to be perfect shapes or drawings on paper. They might be mathematical items like functions. They might even be made up of sets. So we could have a set containing sets. The items in the set don't have to be linked together in any categorical kind of way. In other words, we could have a set consisting of one wig, one cat and one triangle. No reason why not. So the idea of a set is very, very simple, very straightforward. It's a very simple concept. And it might seem that you couldn't do anything with such a simple idea as just a bunch of things. But in fact it turns out that this is at the foundation of mathematics. It took people a long time to realise that. It wasn't until the end of the 19th century that mathematicians started to realise that sets were at the foundation of mathematics, so they are extremely important, even though they're very simple. Usually sets are named by a capital letter. One way to describe a set is to list the things in it using curly brackets. So we can have a set called A, which might contain the integers 1, 2, 3, 4 and 5. Things in the set are called the elements of the set, or the members of the set. And we could say, for example, 2 is an element of A. So that funny sign that looks like a bit like a letter E means is an element of. So 2 is an element of A. No, with a line through it means not. So 6 is not an element of A. Another way to describe a set is to give a rule for membership, as is shown here. So we could say P is a set of elements X such that X is a prime number less than 6. That's the same thing as a set consisting of 2, 3 and 5. The order of the elements of the set makes no difference. So 3, 5, 2 is the same set. Duplicates are not possible. If we have something like 3, 3, 5, 2, that simply says that 3 is an element of this set twice. So it's a pointless description. It's the same as a set of 3, 5, 2. Sets don't have duplicate items. Or we might refer to another set. So if n is the set of natural numbers, we might say that S is a set of elements n such that n is a member of the set of natural numbers and n is less than 7. That would be the same as 1, 2, 3, 4, 5, 6. The set 1, 2, 3, 4, 5, 6 contains 6 elements. We had another set T made up of n greater than 7, then T would have elements 8, 9, 10, 11 and so on. T would have an infinite number of elements. That's okay, sets can be infinite. Or we can have no elements. This is called the null set or the empty set. That's what it is, it's empty, it has no elements in it. So it's usually denoted by a symbol shown here, Greek letter, phi, the null set, the empty set. We can put two sets together like this. This is called the union of two sets. It's simply all the elements in one set together with the elements in the other set. If the two sets have an element in common, like that red star, you don't get it twice in the union, you just get it once. You can't have duplicates in a set, so that would be impossible in any case. So this is a union of two sets, everything together. So union is denoted by this special symbol that looks a bit like a letter U, sometimes called cup. The union of A and B. And that's the rule for it. The union of A and B is a set of elements X such that X is an element of A or X is an element of B. Simple example of union: if S is 1, 2, 3 and T is 2, 3, 4, and the union of S and T is 1, 2, 3, 4. If the union of two sets is the null set, that implies that both sets are the empty set. That's the only way you can get the union to be null. Or we can take the elements in common. I have two sets and we pick out from it the elements which are in both. So the red star, the yellow star and a blue circle. This is called the intersection of the two sets. Symbol for intersection is the upside down cup. So if it's like a U, it's union. If it's not, it's an intersection. And a symbolic definition of intersection: the intersection of A and B is a set of elements X such that X is an element of A and X is an element of B. So for example, if S is 1, 2, 3, 4 and T is 3, 4, 5, 6, the intersection of S and T is 3, 4. The only two items which are in common. If we pick out some of the elements of a set, we can construct what's called a subset. Like here, pick out 3 elements, that gives us a new set, a subset of the first set. So this is a symbol for subset. It's a bit like a less than sign, but it's curved instead of being a little arrow. A is a subset of B. So for example, set 2, 4 is a subset of 2, 4, 6, 8. A being a subset of B implies that if X is an element of A, then X is an element of B. Is a set a subset of itself? Yes. Because every element of A is an element of A, therefore A is a subset of A. It fits in with the rules. But there's an idea that this is cheating. This is not the idea of a set. So the term proper subset is sometimes used. So a proper subset is a subset of something with some items left out of it. So a proper subset is not the same thing as the set itself. Suppose we have two sets and we make some pairs, some ordered pairs, where we choose one thing from the first set and the second thing from the second set. So that if our two sets are 1, 2 and 11, 12, then we can have 1, 11, 1, 12, 2, 11 and 2, 12. Such a thing as that is called the Cartesian product of the two sets. It's a set of ordered pairs where the first one is selected from the first set and the second element is selected from the second set. So here it is again. Cartesian product of two sets A and B is a set of all ordered pairs x, y, where x is an element of A and y is an element of B. This is a visual representation of a Cartesian product. We have the set A of items and the set B of items, and we pick up an ordered pair, each item of A combined with each item of B. We mentioned it would be possible to have a set which is made up of sets. So here's an example. If S is a set 1, 2, T is 3, 4 and V is 5, 6, we can have the set A made up of S, T, V. Now it's not the same as a set B, which is 1, 2, 3, 4, 5, 6, because B has 6 elements in it and those elements are integers, whereas A only has 3 elements and those elements are sets. And we can have sets which contain themselves, so that here we have the set P, which consists of 1, 2, 3 and P. It's a slightly strange idea, but there's no reason why we couldn't have such a set. It contrasts with the set T here, which is the set 1, 2, 3. T does not contain itself. I suppose we have the set S, which is a set of all sets that do not contain themselves. Is S a member of S? Well, if it's not a member of S, then it qualifies for membership, so it is. And if it is a member of itself, then it does not qualify for membership, so that it's not. Oh dear. That was the famous Russell's paradox, named after Bertrand Russell, the mathematician and philosopher, who was the start of the 20th century. It was a big problem because it showed there was a logical paradox in the theory of sets, and yet set theory was the foundation of mathematics. So it meant there was a logical flaw at the foundation of mathematics, which was a big problem. So how to fix that problem? It meant going back to the beginning and re-establishing set theory with a set of precise definitions of what we're talking about. In what we've presented here, we haven't actually defined what a set is. There are no precise definitions, there is just an idea of the group of items. So this started to be called naive set theory, and that's why this video is called Naive Set Theory, because that's what it's about. It's been changed into axiomatic set theory, where there are precise definitions of what we're talking about, and those definitions are chosen such that Russell's paradox is avoided.